So as promised, we're going to continue discussing cosmology. Also, I think I should leave some time if you have any particular questions or things that you want us to remind or discuss during the last lecture. Is there anything like that, or I should just go on as much as I want and wherever I want to go? Just like that. Okay. So we discussed basically the Big Bang. Anyone else want to say anything? Yeah, what? No. Okay. So we discussed the Big Bang. Switch that. Talked about Hubble's law. Talked about the expansion of the universe. Big Bang, cosmological redshift. Then we also spoke about distance measurements. We mentioned that there are two ways, actually more than two ways. I mentioned here two. One was the luminosity distance and the angular distance. Then we go to Hubble's law. L 1 over H0 Z plus 1 half minus Q0 Z squared plus whatever. Which is essentially what Hubble did. So I have this printout. I hope I wrote it. This is taken, I believe, from original Hubble's paper. I hope you can see it. So there is the distance, which was able to measure to 24 nearby galaxies, the redshift, the velocity, and it turns out to be linear at small scales, and this is linearity coefficient is exactly Hubble's constant. Of course, today we get to very deep. And we spoke about the evolution of the scale factor. And we saw that depends on which type of universe we have. Right? For a matter-dominated universe, I of t goes as t to the power 2/3. For radiation-dominated universe, I of t goes as t to the 1/2. And for lambda vacuum, essentially exponential. A to the power plus minus lambda over 3 to 1/2. For flat universe. Of course, it's slightly more complicated because the universe is not only that. But the basic idea should be clear. Then, of course, the energy densities, rho r, goes as a to the minus 4, rho m goes a to the minus 3, rho lambda goes a to the 0. And we specified that today rho m is around 0.3, sorry, omega m is around 0.3, omega lambda is around 0.7, omega radiation is very, very small. But that has not always been like that, because when we went back in time, there was equilibration in which the energy density in radiation, and radiation is really cosmic microwave background radiation, was greater than that of the matter. And the universe back then looked quite different than the way it looks today. Now we're going to discuss today a little bit more in depth of what happened back then and how it affects our structure of the universe today. But first thing which we have to close is observational evidence. So, yeah.
A is a function of time.
Correct.
Do we know what controls the dynamics of it, or is it all explained in the equations there? Do we know what's
We got that by solving Friedman's equation.
Is this
Yeah.
the reason for that, or is it just...
Remember what went into the derivation of this Friedman equation. Friedman equation is really Einstein's equation.
Mhm.
Right? Plus, we had the Robertson-Walker metric. And Einstein's equation is Einstein's equation. We spent half of the semester deriving Einstein's
Assume
equation.
Einstein equation.
So the underlying assumption is that the universe behaves according to Einstein's equation. Point. And then we plugged in Robertson-Walker metric, right? G inside Einstein's equation. We calculated all this. Robertson-Walker metric means that the universe is homogeneous and isotropic on large scales, which is an observational evidence. It is changing with time. That's Hubble showed us. Right? We know that it evolves in time. It's not the same now as it was in the past. That's everything that went into that.
So if I'm accepting Einstein equation, and I'm assuming that the observation of a uniform, homogeneous world, there will always be a function like that which will stretch or shrink the coordinates.
That's a nice thing about math. That's the most general solution that we obtain. Yes.
And these this factor inside the metric is not dependent on the coordinates I'm using.
I mean, A, the scale factor.
Yeah.
No, it multiplies all the spatial coordinates. We made a separation between the time and space. So all the spatial coordinates are multiplied by one parameter, the scale factor A of t.
Okay.
Again, if you say that the universe, one of the underlying assumptions are not fulfilled, then obviously you need to find a different solution to Einstein's equation. If you argue that the universe has a preferred direction, right, so it's not completely isotropic, then it's a different story. Then we have to put this assumption into Einstein's equation and solve and get something else. Observational evidence. So we said that, and you should know that by now, right? Physics is an experimental driven science. In fact, all sciences are like that. So people saying that this is counterintuitive, doesn't match, this theory is irrelevant. It's bullshit. It's meaningless. The theory is an idea, and it is acceptable only because it can explain the world we live in. So this theory of the Big Bang, there are 5 independent evidence that prove that this is correct. What are they? Maybe you know? Yeah, that'll be the second, CMB. I'm going to talk about that in length today. What?
Black hole.
No, talk about the Big Bang. Big Bang has nothing to do with black holes.
Maybe the Hubble's law.
What?
The Hubble's law.
Hubble's law, yeah. So the first thing is Hubble's law. Hubble's law. Right? Essentially this law. Right. That is something which you can go and measure. You measure the distance to galaxies, you measure the velocities, they all recede away from us, and you find this Hubble's law. Hubble was there first. Right? The second is the CMB. What is the CMB? What causes the CMB? So cosmic microwave background. What is it? Where does it come from? Yeah.
It comes from the reality that was in the past, where the matter/radiation was dense enough to be opaque, and then.
What do you mean to be opaque? What caused it to be opaque?
The density. The fact that photons
No.
scatter
Yeah, scatter with what?
with soup.
Soup. Put the flashlight in the soup. No, they scatter with electrons. So what happened is the following. When we go back in time, right, we said A was smaller, right? So now we said that the density of radiation goes to n minus 1. Right? And we said that the temperature, right, goes as the temperature to the 4 goes as the energy density, which means that the temperature T goes as A to the minus 1. Right? So when A was smaller, then the temperature of the universe, T means T gamma. Right? That comes from Stefan Boltzmann's law. It's a black body's radiation. So the temperature was high. Right? Now it starts to increase. Right? And the temperature today of the cosmic microwave background, 2.7 degrees Kelvin. It's nearly very close to the absolute zero. T 2.7 degrees Kelvin. What we measure?
How do we measure the temperature of photons?
It's a problem. What? We're looking at the distribution. We fit it. It's a Planck function.
Feed it to Stefan Boltzmann.
Planck function. You've seen that in your modern physics? Maybe?
Complement
You have seen it.
special relativity in
No, you should have seen black body radiation, something.
Seen.
Jewish.
No.
That's exactly the black body radiation. I'm not. You should have seen that.
We've seen, but we've not talked about cosmic microwave back.
No, that's fine, but it's a black body radiation. It's a black body radiation at temperature of 2.7 degrees Kelvin. Now we're going to discuss where it comes from. So where did it come from? So in the past we said it was higher. Right? Now, atoms. What is the universe made of? Right? Matter is atoms. Dark matter, forget about dark matter first. Atoms. Mainly what atoms? Hydrogen atoms. Right? What is the ionization energy of a nitrogen atom? 13.6 electron volt, right? So if you go back in time, right, the temperature was higher. Increase. When it reaches, it's not 13.6 because this is again a distribution. You don't need to be at the peak of the distribution. You can be at the edge of the distribution. There will be enough photons. So when the temperature reached about 1 electron volt. So if I go back in time, right, this is time. So this is T0 today. This is the temperature. Right, so the temperature goes A to the minus 1. Matter dominated A goes as T to the minus 2/3. So that means to the 2/3. That means the temperature went as T to the minus 2/3, and then as T to the minus 1/2. T to the minus 2/3, and then T to the minus 1. Minus 1. Rough. But anyway, it increased. Right? So when it reached about 1 electron volt, what does it mean? Right. There were no longer, you could not have hydrogen atoms existing. Right? So from here on, so when it's about 1 electron volt, actually 0.9 electron volt, you do the calculation. The idea is the same, right? Then you could not have had atoms. So from here you have atoms. From here you have ions and electrons. Right? If you go back in time, even further, what is the binding energy of the nucleus? Do you know? If you know nuclear physics. It's around MeV. It's roughly 1 million electrons. Okay. So when the temperature was higher than million electron volt, we could not have any more protons, nucleons. So they broke into protons and neutrons. Okay, so here you have ions, and here you have just free protons and neutrons. If you go even further, what are you going to get? Quarks, right? You could not have.
Some level reached Planck scale.
Yes.
When do you do that? Before Planck?
You know what is the Planck scale? It's a 10 to the minus 43
Yes,
seconds.
but
As we said, this is where physics will not begin. This is way after. Okay. Let's do things on right now, one step at a time.
is it before quarks or after quarks?
No, way before. Way before. Again, this is the earliest that known physics can handle. Everything before that is speculative. It's not part of the physics we understand. And quarks is something which we do understand. But you see the idea here. So, temperature here. Now we talk about the soup. Right? What is the soup? We had protons, neutrons, or ions, and electrons. Now electrons are very good scatterers. Right? The cross section for scattering between electrons and photons is Thomson cross section that you may or may not have seen. And I don't know if you've seen that. Of course, in the particle physics, and you've seen it. I don't know where else you've seen it. What?
Introduction to modern physics
Okay,
and
that's
classical mechanics.
So when you have when you put electrons and photons, then they scatter.
You also had the question in the homework about Thomson scattering and
Particle
maybe.
physics.
No, that's a question of
In the homework, like
So
one
Compton scattering, yeah, it's all the same cross section basically. Now, but with atoms, they're not good scatterers of light, right? This room is full of atoms, but the light just goes through them unless there is a cloud, but that's something else. So here there was a cloud, and here there is no cloud. Right? So what I mean, a cloud, there was continuous interactions between photons and electrons. And so if you were here, you could not live here, but you couldn't see anything because there was just like, a soup, just like driving inside a cloud. You can't see anything. But once the temperature drops down sufficiently, then the electrons recombine, so it's called recombination, recombine with the protons, producing the atoms that we have. And what happens to the photons? They're free to move. And where are they? They're still moving. They're still there, all over us. Isotropic. So that's the cosmic microwave background. That was, so this is, we've mentioned, this time is called recombination. I'll calculate it shortly. And 2.7 degrees Kelvin is frequencies, it's 160 gigahertz, which is the microwave. It's a microwave regime. It's not too far from where your microwave in the kitchen works. And okay, the story is it was predicted by Ralph Alper in '48. He never got a Nobel Prize for that, no reason why. And then seen by Penzias and Wilson in '66 or '67, and they did get a Nobel Prize for it. Okay, so that's the second, CMB. What's the third? There are more. We said there are a few independent evidence. What's the third one?
Inflation.
What?
Inflation part in the...
No, inflation we don't know. It's an idea that is there to help solve problems, but we don't have evidence that it exists actually. But I have evidence for the whole story of the Big Bang. So cosmic microwave background, there's no other way of explaining that. Hubble's law.
Maybe
You've seen?
the anti-symmetry between matter and antimatter.
No, spontaneous symmetry breaking is a different thing. It's a big question by itself. We want to. I I did not prepare anything to discuss that here. So. What are we made of? What? Atoms, right? Most of us are made of atoms. Most of us. And where are the atoms made? Where are the elements made? What? In the stars, right? Most elements are made in the stars. But where did the elements that got in the stars were made of?
Other stars.
What? Other stars, yeah. And then before them? Actually, that's true. There was other stars. There were 3 populations of stars, 3 generations of stars, as we know.
Fusion?
Fusion of what?
Of protons and of baryons against baryons.
Right, here. That's called Big Bang nucleosynthesis. And that's called primordial abundances of light elements. Primordial abundances of light elements. So if we look at the universe, what is the universe made of mostly? What? Hydrogen, that's true. What else? Helium, right. And what's the ratio of the hydrogen to helium? About 1 to 4. And okay, so this is something which we can actually calculate.
Wait, the ratio in the
We can calculate this ratio.
The ratio of occurrence of
Yes, of abundances, exactly. That's called the primordial abundances of light elements. That's also called Big Bang nucleosynthesis. That's the other name. So basically everything that is heavier than lithium is made in stars. But up to lithium, the lightest elements are made here in the Big Bang. And we can calculate. I won't show you the full calculation because it's a bit technical, but I'll show you the basics ideas so you can do how to calculate that. We know what are the ratios. So if you look at the ratio of helium-4 to hydrogen, this is 0.245. That's a predictor. And then also to deuterium to helium, and that's primordial. And primordial is much smaller. It's something like 10 to the minus 5. And helium-3 to helium, primordial, again something similar, 10 to the minus 5. And lithium-7 to helium is for primordial is something like 10 to the minus 11. Again, these are predictions and they are measured.
That means that the total mass of all helium and the total mass of all hydrogen is about the same.
What do you think?
There isn't.
You can calculate. Yeah, well, we're going to do that. We're going to calculate the rates of that.
What are the assumptions that predicted by?
We're going to do exactly what we have here.
Okay.
That there is an evolution. I'm going to show it to you. That is what we're going to show. That there is an evolution in the scale factor, that they are coupled as long as the rates of interaction is faster than the expansion rate of the universe, which is 1 over Hubble constant. This is the third one, again independent of the others. I said 5. 2 more. Any ideas? Maybe. So the fourth one is galactic evolution. So that you may not know. So galaxies, like other creatures, they have life. So like if you look at a person, you can roughly tell if it's a young person, baby, young, older person, just by the look, because they look differently. And the same for galaxies. If you have younger galaxies, they look differently than older galaxies in various parameters. The rate of star formation, the amount of hydrogen and helium you have there, their shape, the spiral galaxies versus elliptical galaxies. There are various things that discriminate younger galaxies than older galaxies. And when we look at the far distance, we're seeing galaxies that are younger than the galaxies that we see close to us. And also galaxies that are in the really far distance, they look differently than young galaxies in our nearby universe. I don't know if there's much point in getting into that without getting too deep into astronomy. One thing which I should have mentioned, right? If we go back here, right, we said that before this recombination, photons and electrons and ions were fully coupled, so nothing. It was like one big soup, as you call it. And then at this point, electrons and protons essentially recombine into atoms, and the cosmic microwave background escape. So this is, by definition, the first signal that we have ever in history. Then what happens next after that? So this is a redshift of more than 1,000. What happens after that? What? Yes. Well, structures formed. Matter was already there. Atoms were formed, but then it took time for what?
Matter clumps up.
Yes. So matter clamps up. The fifth is actually, we see this imprint of the cosmic microwave background. I'll discuss that in a second. And so there was a period. So matter, starts, gravity starts to act and compress the matter until the first stars form. And this, of course, took time. So this is a redshift of about 1,200, 1,180 to be precise. The first stars that we see, do you know what redshift? First stars, no. So matter fall in, form stars until you start have less.
10 tenths?
About 10 to 15. So let's say 20 is the first ones. The first stars, the first galaxies around that region. That's because of James Webb Space Telescope. Before that, we knew only up until roughly 9. Now we know it's about let's say up to 20. That's what we believe there. So all this region between here and here, there was nothing that emitted light, right? This is
we don't see them, but do they exist?
There was nothing that emitted light, right? So that's called dark ages. We don't, because there's nothing that produce any light, and from 20 we start seeing the first light-emitting objects. Now there is what's called 21 centimeter cosmology, which is related to flip of the spin. That's radio observations, and there is still it's very promising, but there is still no data available. So I won't talk about that. That's to explore this region. So this is the dark ages. Finally, before I answer a question, what's the fifth independent evidence? But again, you don't know that. That's called baryonic acoustic oscillations. BAO. Baryonic acoustic oscillations. That's a little bit, I'm stressing it, but I hope to have enough time to talk to you properly about that. The basic idea is the following. So we assume that there were some initial fluctuations. So it's not exactly homogeneous, but there were some small initial fluctuations. And then gravity acted, and when there were regions which were slightly denser, they were start to attract more and more material, which eventually formed the galaxies that we have. Stars and galaxies, that's the structures that we see in the universe today. Right? We know that there are galaxies, so there is structure. Now, this started to act right away. So even before this recombination, there were these fluctuations, which we believe were on all scales. Right? Now, but before the recombination, when there was some regions which were slightly more compressed, that means that there was a higher photon pressure. A bit similar to why our sun is steady. It's not moving. So if you try to compress it, then the photons push it backward. So what happened was that there were some small oscillations, right? And they occurred on all scales. Until when? Until the photons decouple. Right? When there was decoupling, there was nothing that give a restoring pressure. Right? So what you'd see is that you see these fluctuations, and they will be frozen at this decoupling. Where do we see them? No idea? We'll see them imprinted on the cosmic microwave background. When we look at tiny fluctuations, it's very, very small. Cosmic microwave background fluctuations are of the order of 10 to the minus 5. Right? So it's 2.7 degrees. Add up more, and delta T over T here is around 10 to the minus 5. So they were predicted a long time ago, but they were only observed around 25, 30 years ago, because the instrumentations became sensitive enough to detect this delta T over T. And you see that when you look at correlations on the cosmic microwave background. So I really hope that the last 10, 15 minutes of today's talk I will show it to you how you get this information. Right? So this is imprinted on the fluctuations that they are detected on the cosmic microwave background. Yeah?
The cosmic background radiation, we don't see it's 2.7 because we have Doppler shift, so it's gonna...
Doppler shift is of 10 to the minus 3.
Minus 3 is
Doppler shift. When we look,
but I mean, how can you measure an error of 10 to the minus 5 when you have Doppler shift?
when we look, that's what you see. Okay, that's what you see. Now, if you are very sensitive, you'll see that. That's a dipole. That's a delta T over T of around 10 to the minus 3. And that is because of the motion of the Earth around the Sun around the center of the galaxy. Now, when you correct for that, that's what you're going to see. And that's of the order of 10 to the minus 5. Okay? In the newer, more sensitive satellite, you'll see that. These are the fluctuations that you're actually seeing. And the dots here represent changes in the temperature. So each one is a black body, but at a slightly different temperature. So the difference between that point and that point, delta T over T, is around 10 to the minus 5. Okay, is that clear? Once we have this data, we can now analyze it and understand what it tells us. I hope I'll show that to you towards the end of this lecture. Yes?
You say that the Doppler shift, which is neutralized, it comes from Earth around the Sun and Sun around the galaxy. It's not coming from the motion of the galaxy also?
Maybe, but it could be. It's small, but if it will be, it will be towards the Andromeda.
So
or around the center of the cluster of our local cluster.
Okay. And the temperature, the radiation we get now was emitted by emitted long time ago, right? So is there a cosmological redshift? So
yes, that's why it's 2.7 degrees Kelvin.
So
when it was emitted,
yeah,
it was at around 1 electron volt. So you can calculate how much is that in degrees.
Okay,
that should
so,
be
so it would be hotter.
Way hotter.
Okay, so
there's a funny filter.
There's a hot temperature, and right now we absorb it as a low temperature, and so this is the observation. And I guess we observed the whole profile of the black body, right?
Yes,
so
of course.
you know
it's a black body. It's a nearly pure black body.
So black body radiation also depends on Planck constant, in a way. The curve.
It's a Planck distribution, you mean?
Sorry?
It's a Planck distribution.
There's Planck constant in the formula which turns off the high energy.
It's a wind spectrum.
Sorry?
It's the wind part of the spectrum, right? There is an exponential.
Yeah.
Yeah.
So we could, if we look at the profile of that and fix for the cosmological redshift, we could find out if Planck's constant was the same as ours today.
Yes, we do not question it. So yes,
yeah,
we don't have any evidence.
As
part of the theory, we do not. There is no evidence that any of the constants of nature evolve in time.
But yes, in energy.
What?
But yes, in the energy, along the energy spectrum.
No, constants of nature such as h bar or c or g, we don't, in this theory, we do not assume anything about it. They are not constants.
When we measure, can't we say?
You're right. I mean, both of you are right. I mean, this theory is not assuming any time evolution of the constants of nature.
CMB is not a theory; it's an observation.
Yeah, what you see, you're observing, you're looking, and you're seeing a black body, a nearly perfect black body, up to 10 to the minus 5, isotropic everywhere we look. At this temperature. That is what you measure. Point. That's Benzias and Whitson. Okay. Now, how do we understand that? At 1 electron volt, let's do a quick calculation. K Boltzmann T, right? It's 10 to the minus 16. K Boltzmann roughly, right? Electron 10 to the minus 12. So we're talking about temperatures of, well, we can actually do it, 1200. 1200 times 2, that means that the temperature there was around 3000 degrees Kelvin.
So this gives us, for example, an indication of when did this happen, right? Because we know the energy of when the matter becomes transparent in photons.
Yeah, it's the same thing.
We know the curve of the energy going down.
Mm-hmm.
I mean, it is not even related to the Big Bang. Even if the Big Bang will be discovered to be like, instead of 14 billions, it will be...
No. But how do you explain the existence of a cosmic microwave background in a theory that is not a Big Bang? I mean, you have a set of observations. What I'm saying now, how do you know that I'm not telling you very nice stories, mathematical, very nice, but they got nothing to do with reality. So this is the reality. These are things that we actually measure. And these are all consistent with the predictions of the Big Bang theory. Right? So yeah, again, it's a theory. Maybe it's incorrect. Maybe there is a better theory. But if you have a better theory, it will have to also explain all these observations. Plus explain where it differs than the Big Bang theory. Yes?
Why, when temperature was so hot, things like suns, if we know that the temperature at the center of the sun is much higher than the temperature then.
What do you mean by that? Temperature kept on growing. It depends when you say then.
At the equilibration, for example.
We know what the temperature equilibration is.
Yeah, we know this temperature. It's around the temperature at the surface of the sun.
Maybe
we know that the surface of the sun doesn't decompose, right? So why?
What do you mean doesn't decompose?
No, not decompose. Doesn't fall apart, right?
Why would it fall apart? We're talking
Well,
about
so
different things.
why-
I'm just saying that if you take, we're talking about plasma, right?
question is
If you
why-
take a box,
Yes.
right, and heat it,
Yes.
when you reach a certain temperature, you will no longer have atoms in it, right?
But
Because the atoms will turn into electrons and protons. The same thing happens in the sun.
Yes.
In the center of the sun, it's much hotter, right? So that's where you have nucleosynthesis, right?
Yes.
It's exactly the same thing. There's no difference.
So when did you get suns or stars at that temperature?
You don't have time to. What do you mean? You don't have time to reach stars, right? To reach stars. What is it? What is a star? It's a bunch of gas that collapse together because of its own self-gravity.
Yes.
That's in the course of astrophysics, right? Not in the course of geography. It collapsed, and because once it collapsed, the pressure inside got so high, the energy density got so high, so the temperature increased, and essentially it reached a level in the center of the sun of more than MeV range, and then you can start processing new elements.
So if the temperature was so hot, so the gravity was so high, right? Then because
Gravity was so high.
everything was concentrated in a very small
Yes.
area, right? So,
But
but it's
there was an expansion.
accelerated.
No, there was an expansion there, right? The universe was constantly expanding.
Yes.
It did not have the time. Like, it did not have the time to form stars yet. Like, gravity did not. It takes time for the proof of gravity. And there we said it could not have because there was a photon pressure. So when gravity tried to pull matter, it also pulled photons, and the photons, that means that there was a higher photon pressure which pushes it back.
Oh.
Which is exactly the reason why our sun is steady. It's not expanding or collapsing. Okay? If it tries to expand, what happens is that it slightly cools down, then it tries to shrink, increases the radiative pressure, which pushes it back to where it is.
Does the generosity pressure also affect the sun, or is it to the
We're doing the generosity pressure. Of course.
לא,
Matter is the same matter. That's again, this is the nice thing.
השאלה היא ספציפית בשמש, האם הוא זניח, הוא זניח דרסטית ביחס לשאר הפרמטרים?
מה זאת אומרת זניח? When you let's do the calculation. No, it's very important.
הסן הייתה קורסת אם לא היה לחץ טיפה?
Okay, sorry, you're talking about לחץ ניוון, the generosity pressure, or you're talking about photon pressure? Right now it's the photon pressure that is dominating. So what keeps the sun steady is a photon pressure. Yeah, of course, it's a photon pressure. Now, what is the nice thing about these things? We know the rate of nuclear reactions. We know the rate of nuclear reactions from laboratory experiment. Right? We apply the same rates to what happened here. Now, nobody was there. But we're assuming that the rates are the same as they are in laboratories, and we get the right results. Right? So it's a very good indication that the physics today and the physics back then was the same physics. Otherwise, why would you get the same results? Now let's look at that. Okay?
איך אתה יודע את הסקאלה צמדים שלו? כי לא נראה לי...
I do know that. We said that, right? We know how we know how the scale factor evolved is time.
אבל זה כבר תיאור, איך אתה בניסוי כאילו...
בניסוי אני לא.
אבל איך אתה יוצא את הפלוט הזה מניסוי?
No, this is theoretical plot. It's a theoretical plot.
זה פלוט תיאורי שמסביר את מה שאתה...
This is the observation, right? This is theoretical plot. It just matches. Right? I mean, I didn't get the scaling laws I got from the theory, right? From how A evolved in time.
אבל זה לא שמדדתי את התרשים הזה בכל התיאוריה. הוא מסביר משהו אחר שם. הוא מסביר את הווקטור.
This explains that. Macro-quantum radiation explains that, explains that, explains everything. Okay. Thermal history of the universe. That's a little bit more technical because it requires some knowledge of statistical physics. So I don't know, I assume you have it, but I'll get you through that because the results is quite fun. There is some technicalities there which I may or may not go through. It's in my lecture notes. Not necessarily the one that you're seeing if you're looking at my open source, but there will be in the lecture notes that you'll see in the I post them today. So thermal history of the universe. History. Okay. So one of the things we want to see is how to calculate the ratio of light elements. And we said about 75% of the light elements is hydrogen, 25% is helium. Okay, and then a few fraction of lithium. Now we said we had the equilibration between matter and radiation, right? So Z equilibration was about 3.6 times 10 to the 3. So at smaller redshift, Z smaller than Z equilibration, the universe is matter dominated. And at higher redshifts, is is radiation dominated. So this we know from the current observations and the theory of how it evolves. And we know that the temperature T at equilibration was approximately 1 electron volt, and T also goes as A minus 1, which is 1 plus M. This we know. Now, so we said when the temperature was greater than a few electron volts, then we could not have had any could not have had any atoms. When the temperature, so when T was greater than about 1 eV, no atoms. Do you know what is the mass of the electron in electron volts?
0.5.
Right, it's about half MeV. So when T was greater than about 0.511 MeV, that's the mass of the electron. And what does it mean? What?
It generates
Yes, so we had a lot of pairs of electron positron pairs. So pairs, A plus minus pairs. So photon goes to A plus A minus, because they could have done that. So the basic idea, and when it was more than a few MeVs, and we had no more protons and neutrons. Now,
does the sun generate lots of electrons and
inside.
protons?
Do we measure it? No, because by the time they reach out, and the temperature goes down. There is the interior of the sun, the surface of the sun. We're looking at the surface. Okay. What we look as a distribution function. So the distribution function F species A of P and T. Right, I don't need the location. So the basic idea. There are many particles, and they constantly interact with each other. But there are many particles, many different types of particles, which constantly interact. But typically they are relativistic. So the rate of interaction gamma is approximately the density times the velocity times the cross section, which is c. Right? So as long as the rate of interaction is greater than what? No. That's a rate of interaction, so it's 1/7, 1/time. Then h of t, which is a dot over a. What is that? It's the expansion rate. And the expansion rate. Right. See what happens, right? I have a box. I have plenty of particles that move relativistically, and they constantly interact with each other. But my box expands. Right? Now, what happens? If the interaction rate is very high, then what can I say? Decreases, yes, but if it's higher than the expansion rate, what does it mean? That they maintain the thermal equilibrium. And And I can safely assume that all these particles are in thermal equilibrium. Right? And if it gets lower, that means that they are decoupled. I can neglect them. I just leave the. They don't interact anymore. Of course, there is some exponential decay, but that's what people really want to do, fitting with the C. So if it is as the rate of interaction gamma, if it's greater than the expansion rate, then we have a thermal equilibrium.
So I can just say it's like an ideal gas. Or what does it mean?
Yes, it's ideal gas, but what type of gas? What? We have bosons and fermions. Fermions and bosons, right? So what is the distribution function of fermions and bosons? Right, so we have distribution function Fa, distribution function of P and T, dP, dQp, is Ga over 2 pi cube times 1 over E to the power E minus mu A over Ta plus minus 1. Right? So plus 1 is for fermions, and the minus 1 is for bosons. Yes.
Thermal equilibrium means temperature is constant, right?
Yes. Now it means that it's not constant in the sense that all the particles have the same temperature.
Okay.
Now, most of the particles that are in the universe
the
are
temperature of all types of particle is equal.
It's equal. Equal to what? Temperature of the photons.
Okay.
Temperature of the photons is what we call as the temperature of the universe.
The cosmic ray.
Photon essentially is cosmic microwave.
Yeah, it's supposed to be dP cubed.
What is G?
Degeneracy.
What is mu?
The potential.
Potential. And the potential is the energy, it is the temperature. What?
How units make sense?
What?
How is potential described?
I'm going to neglect it. I'm just going to assume it can be going. Yeah?
How units make sense?
Yes, they do. Leave it up. You want to have a K Boltzmann, otherwise normalize to the right units.
Okay.
Right?
K Boltzmann, and then
Then
it
that's
will be in units of energy.
Now EP, yes. EP,
No, but E.
don't worry about it. The units are not the issue. Okay?
Okay.
Just normalize to the right units. EP, right, is P squared plus M squared by 1. Yeah. That's the energy of a particle with momentum P.
It's E times mu, E minus mu.
Mu, minus. But
Okay.
again, I don't care because I'm going to assume that
It's a minus sign. Okay.
Happy?
What is the line next to the E?
What is what?
In the equation, there's a line next to the E. You know, like
EP minus mu
yeah,
A
and
divided by
above the
TA.
P, next
1
to the
over
Never mind.
what?
No, the
Plus
line
minus
above
what?
the P. You
It's a
have a
vector,
line
vector.
next to the.
It's a vector.
Okay.
It's the same magnitude.
Yeah, all right.
Okay? Now, what do we say? We said as long as the interaction rate is greater than Hubble time, then these are in thermal equilibrium. When it goes down, they get out. When did they get out? It's called decoupling. So, universe expands. That means that T decreases and decreases, And so we have a decoupling, so gradual decoupling.
T decreases because the photons are getting.
T decreases because the temperature goes as a to the minus 1. A increases. T decreases and decreases, gradual decoupling of the particles from equilibrium. Of course, each particle has its own mass, so each particle will decouple at a slightly different time. Okay. And remember, I told you there is a connection because this will be imprinted on the ratio of masses, the ratio of abundances of elements, also on the cosmic microwave background. And from that we can learn about particle physics, about what types of particles could exist in the universe. And again, surprisingly or not, it's the same particles that we know today that we've seen, we deduced their existence. Okay. So once they decouple, then they simply, they don't no longer interact with other particles, and what do? Just move along geodesics. Move along geodesics. That's it. That means that the distribution function freezes. So if you call the decoupling time at t equal td, this is the decoupling time. And a equal ad is the decoupling a. Then we get that f decoupling of p and t is equal to f integration at p a of t divided by a. Simply states that this is the momentum goes down as a of t divided by a.
Decoupling happens before or after equilibration?
It depends on the particle, but mostly before. Okay. If we have this distribution function, now what will be the density and energy of the particles? Which you might have said. Pretty much sure that you've seen that before. So what is the density? If I give you the distribution function of a particle, from a distribution function, how do you get the density?
10 times.
What?
Its distribution function is a function of n.
Should
right?
Integrate
N times
f of p dp.
t.
Right?
Isn't the distribution function also dependent on the number of particles?
No.
If you had the EP minus mu n.
I have to have mu a. I have to know what is mu. It's fine.
Probability of finding
A is
particles.
what?
So essentially, guys,
A is what again?
but mu a is just for the species. Right? For different particles, I just write them with a, which I just now remove it because I don't.
Distribution function is not dependent on the number
So
of
for up quark and electron, it's not going to be the same. So just to discriminate between them. So that's going to be g over 2 pi squared integral from the mass to infinity of e squared minus m squared half e dE over e to the power e minus mu over t minus plus or minus 1, depends if it's a fermion or boson. The energy density is integral of f of p times e dq t.
From where you got that factor of e squared minus m squared? Oh,
This is
it's
P. This is p.
yeah. Okay, I see. I see. Okay, thanks.
G over 2 pi squared integral from m to infinity of e squared minus m squared 1/2 E squared E over E minus mu over T plus minus 1. Here's a pressure which we don't need. Now, of course, if I'm talking about very energetic particles, so for T much greater than M, so that means that they're relativistic. There is no degeneracy. So that means that T is much greater than mu. So I can forget about these terms. And we get that rho is approximately G over 2 pi squared times integral from M to infinity of E cubed E over E over T minus 1 plus minus 1 depending. Okay, which is, you just go in a mathematical textbook. I actually did that. You can look at the solution, which is for bosons, G bosons times pi squared over 30 times T to the 4, that's for bosons. And for fermions, it is 7 over 8 G fermions of times pi squared over 30 times T to the 4 for fermions.
When you neglect all mass, when you assume it's from 0, if you remember.
Yes, essentially yes. I assume it's relativistic particles. I neglect the. Yeah.
The temperature is evaluated at the time of decoupling, right?
No. Temperature is temperature. I'm looking at the rho generally for the given temperature. What is the energy density?
Okay, if you want. No.
The condition now is that it's much greater. It's asymptotic. Okay. When I get to temperature is approximately the same as M, of course I need to do the full integral. I cannot allow myself that, but then it's going to be more messy.
We said we need to take the distribution at the time of the decoupling, right?
No. At the time of the decoupling, if I know the distribution at the time of the decoupling, I know the distribution at any other time. That's called freeze out. So once the particles decouple, the distribution is cannot change anymore because they do not have any more interactions.
Even if the temperature changes, right?
Okay. The situation is the following. As time goes by, this is the temperature of the universe. So this is the temperature of the photons, which is essentially the temperature of the universe. Right? And it goes down with time. Right? Now, we have different particles. Let's say, for example, protons. Right? Energy of protons would be around GeV. So if the temperature reaches GeV, proton is a bad idea. Let's look at muons. Right? Muons, the energy of muons is 140 MeV. Right? So once we reach 140 MeV, right? We had muons, so there was muons, T muons. Right? By notation, but muon. And they were decoupled. They had the same. They kept on having interactions with the photons and with all the other particles because they were relativistic. Right? If the temperature here is way above that, they had Lorentz factors of a lot. Right? Thermal temperature divided by 140 MeV is the Lorentz factor. Right? So they were coupled to the rest of the universe until the temperature drops down, and then they became decoupled. Right? When they were coupled, their energy density, muons or fermions, we have like that. For any given temperature, this was their energy density. Right? Now, of course, when we reached very close by to this region, then there was some evolution because this equation needs to be solved exactly, not using the approximation that I was doing here. Fine. Okay, don't get into this small detail because it's really a small detail. If you want to do exact calculation of what is the exact abundance, you get some correction, of course. It's a small correction.
Okay. So this means that at the time of the decoupling, the density was like this.
That was like that, yeah. And then it did not change. It just the distribution function.
So T muons flatten out.
Essentially, yes. It's they just got this is their rest mass energy, 140 MeV. Then their temperature they became non-relativistic essentially.
Okay.
Right.
So this is the density at the time of decoupling. What happened to the density after that? Stay the same, or does it fall?
It just fall down like like all the other non-relativistic. It became non-relativistic.
Okay, so
It's a non-relativistic matter, and then it just fall down as all the other non-relativistic matter.
it goes as a to the minus 3.
Yeah.
That one?
Yeah.
Okay.
That's all.
And
They became part of the non-relativistic matter that there is still there to be.
And how do you find the genus?
I'm going to show you that in a second. That's actually you're supposed to learn in some other courses. G, you mean? I'll show you that in a second. That's not the main issue. Okay. So essentially, we can write this down as rho total. So this one we have, I can write it down as energy density, total energy density, rho total, right? Just G total times pi squared over 30 times t to the 4, when G total is sum over all the bosons, Gi times Ti over T. And 4 plus 7/8 sum over all the fermions, Gi Ti over T to the 4. The pressure is roughly rho over 3. Pressure is roughly rho. When we, this is, as long as they're relativistic. If they're non-relativistic, then we're in the, you have this exponential decay, and then they really decouple. Okay, now, I'm not sure that you're, don't look that happy. Now let's see what happens. In the radiation-dominated area, we have that A dot over A squared is H squared of T, which is also 1 over 4T squared, right? Because A dot is A over dt. And H squared is 8 pi G over 3 rho. And when I look now at the total rho, this is 8 pi G over 3, and rho is just G total, it's just G, or just G, times pi squared over 30 times T to the 4. That's rho, that's the energy density. Photons are included. Now I can scale that with the Planck energy. So E Planck is square root of H bar C5 over G. Since in the units we have H bar is equal to C is equal to 1, then I can write down M Planck is G to the minus 1/2. This is about 10 to the 12, 10 to the 19, sorry. GeV, so 10 to the 28 electron volts. We can write down H of T is 1.66 G to the power 1/2 times T squared over M Planck. And the time, here I can write T is around 0.3 G to the minus 1/2 M Planck over T squared, which is about 1 second for T over 1 MeV to the power minus 2 g to the power minus 1/2 second. What does it mean? The production of all these elements happens at around 1 second. Yeah.
From where we got that h bar, just unit analysis? I'm not talking from where we got the Planck energy, but why we use
It's called natural units.
what?
That is called natural units.
So
It's like we're using here
we
C
had
equal
the
to 1.
h bar somewhere there.
In natural units, you know, rather than writing down g, I express the value of g with m Planck. It's just choice of units.
Yes. Yeah, but what I'm asking, where in those equations you got h bar? Where
No. Yeah.
it from
I have here
statistical
from
mechanics?
this is from Hubble's law, right? H squared is h by g over 0. That's basically from the definition of Hubble's constant.
Yes.
Now I said, okay, I have g here. G I want to express. I could express it in any units that I want, but it's best for me, or easiest for me, to express it in natural units. Natural units is Planck units. So Planck mass is h bar c5 over g. That's where
Yeah, that means before h bar were in g or in something, but
no, h bar was never. Just introduce it now as a rescaling, putting the units. Now you don't have to do it. I mean, you can put whatever units you want for g.
dimensional.
You'll still get
analysis.
it's dimensionless. You still end up with 1 second.
Why? What does it mean? Why does this mean this expression, the creation of particles of 1 second?
Well, let's see that, right?
Wait, why is massive?
We don't know what G is and don't know what's.
First you do know.
in one
Okay.
one mega involved because that's what
Okay.
we like.
Now let's.
Tiny and-
Let me explain. One step at a time, you'll get it. If I try to rush, then you'll not get it. If I do it slowly, you'll get it. So now let's look. If we have, we have to look at the temperature. So if T is smaller than MeV, right, then the relativistic particles that there are three neutrinos and 2 photons. Maybe that is the place that I need to. So if I put it in the appendix, I'll just do it quickly. So within the standard model, 17 particles in the standard model, right? 6 quarks. Up, down, charm, strange, top and bottom. We have 3 colors, spin half. So what is the degrees of freedom? And each particle has an antiparticle. So G is equal to 6 times 2, right? Particle, antiparticle, spin half, another 2 times 3 colors. Overall, 72 for the quarks.
Oh, so it's degrees of
It's the degrees of
for a
freedom.
single quark, right?
Yeah, it's degrees of freedom. We have gluons.
Quarks come with no quarks come with sets.
Each one of them have different masses, so I'm a little bit cheating. I'm just putting them all together.
Each one aren't the quarks that come with a fixed car or a fixed spin or something. Choosing the degrees.
Yes, it's degree of freedom. That you have to learn, of course, in the standard model.
It hasn't.
gluons,
The
G.
masses are very much.
Masses are in the range of between MEVs to G.
Very far.
MEVs to G. Yeah, I'm looking at the temperatures. Gluons, the masses of they have masses to 100. The most heavy one is the bottom, which is 175 G. Gluons, there are 8 of these, and they are bosons. They have spin 1. So their mass is bosons. Spin 1, so that is 2 degrees of freedom. Overall, 60.
How 2 degrees of freedom?
3.
Mass 3.
That's right.
Mass minus 0.
Okay, that I need to check out.
1 minus 1
They are massless. Okay, I know it's 2. I have to check it out. I don't know.
Massless
Leptons.
particles lose the 0 spin.
I think that they will lose that, so they should have a 2. But yeah, I know that the result is correct. I have to see why. Leptons, again, we have 6 spin half. So total, we have 12.
We have 6, but we also have the anti.
What? Yeah, okay, sorry. 12 plus 12, right? So leptons, we have the electron, muon, and tau, and then we have the neutrinos. No, sorry, the neutrinos. E minus E plus, mu minus mu plus, tau minus tau plus, spin half, 12. Then we have the neutrinos, neutrino, E, neutrino E bar, neutrino mu bar, neutrino tau, and neutrino tau bar. They're also spin half, but they're all left-handed. We don't have one which are not left-handed, so we only have 6 degrees of freedom.
Left-handed means spin up.
What? It means helicity is always the direction of motion.
Helicity?
Physics course.
You have to take a course in quantum physics. I cannot do it in humans. Then we have the electroweak gauge bosons, right? So the W gauge bosons. We have the W plus minus the Z. 0, so they have spin 1. They are massive. Yeah, that's spin. They will be massless, so that's why you have 2. So you have 3 degrees of freedoms for each one. Plus we have the photons, which are massless, so G is equal to 2. So here we have 3 times 3, that's a 9 plus 2, so that's an 11 total. And then there is the Higgs boson.
Do photons have spin?
Yes, spin 1.
Anywhere? And
They have polarization. They have 2 polarization degrees.
this is equivalent to an
So
analog.
you can think of it as that is, but they are massless.
And this is
Then you have the Higgs boson, which adds 1 degree of freedom. So overall, G fermions, you have a 72 plus 12 plus 6. That is a 90.
16.
No. This is a gluons or bosons.
Only
And then the G of a bosons is 16 plus 11 plus 1.
Why do you count them all in the same?
Oh, that's the right question.
They have different.
If the temperatures are higher than the most massive particle we have, then we should count them all. But if the temperature, as the temperature goes down,
They're
we
all
don't need to
distinguishable.
count them. What?
They're all distinguishable.
Exactly. Then they start to decouple. So when we reach a temperature less than MeV,
Even if they are coupled, they're distinguishable. They have different masses.
that's what I'm saying. If you're looking at temperature which is much less than MeV, the only thing that are still relativistic would be 2 photons and the neutrinos. Anything else would not be relativistic anymore,
Okay.
right? So once we reach that, then we can say that G is 2 for the photons, plus we had for the fermions, we had 7/8 times 3 times 2. And there is another one which I won't have time to show you that, and that is that the T of the neutrinos is 4/11 the T of the photons. So we also have 4/11 to the power 4/3. That's because T neutrinos is 4/11 to the power 1/3 T of the photons. That you can get, so this is around 3.36. That is from conservation of entropy. I'll put it in the lecture notes, so you can do it now. It's a technical calculation. Yeah?
If we will find more elementary particles and all of those stuff, all of these calculations will be wrong.
All of this calculation will not be wrong. We'll have to modify because you add up
Yeah,
another degree of freedom.
we will have to modify.
But you will see that. Where will you see that? In the cosmic microwave background fluctuation.
Mm-hmm. So
Which we don't
if,
see.
for example, we had gravitons,
Uh-huh.
something that we are not expect to have, we will be able to say, okay, maybe we have gravitons, here is an observation.
Correct. That's why you can look at the cosmic microwave background and deduce properties of elementary particles in the standard model. That is the whole point of the exercise that I'm doing here. Right? Yeah.
So you're saying this, that when the energies are high enough, the distinguishability isn't black and white thing, and we need to count everything that has.
What I'm showing you is just the basics of. What I'm showing you is just the basic. You actually have to solve these integrals for the exact temperature. People do that. Some people do that when you get this. That's course, but you get the basic idea from here. I hope. Now, if the temperature is higher, so this is if you have a temperature which is, earlier times, the temperature is, let's say, much higher than MeV, much less than GeV, or 100 MeV. Right? So now we also have electrons and positrons. And electrons and positrons, the relativistic particles. So I have 2 more fermionic degrees of freedom. So we end up, the G should be 10.75. If the temperature is much greater than 300 GeV, then we have all species here. Then we have the G is 106.75. So the degeneracy changes with temperature. So now we finally can see the full picture. And the full picture looks like that. This is time. This is temperature. So the earliest time from the Big Bang that we can say something meaningful is the Planck time. Right? So M Planck is h bar c over g power 1/2. That is, let's say, 10 to the 19 GeV. And the corresponding time, T Planck, is h bar over M Planck, c squared. That's h bar g over c to the 5 1/2. That is 10 to the minus 43 seconds. So that is here. From the Big Bang. We have gotten the temperature of the universe was 10 to the 19 G. There is nothing we can say before that that makes any physical sense according to the physics we understand. The next is at around 10 to the minus 38 seconds. The temperature drops down to around 10 to the 16 GeV. That is known as the Good scale. We did not touch it, not even in the particle physics course. That's called the Grand Unified Theory. That is the time where we believe there was a spontaneous symmetry breaking, and that's where the Higgs started to couple to the other particles to give them their mass. Right? So that's about the time, 10 to the minus 38 seconds. The interesting thing is from here on we do understand. When we do go to physics, we understand quite well. Now, at the time around 10 to the minus 5 seconds, the temperature of the universe is now around 100 to 300 MeV. What happens here? That's where the gluons couple together with the quarks to produce the baryons, protons and neutrons. That is a production of baryons. When the temperature drops down to something like between 10, 0.1 to 10 MeV, that is times of roughly in between 10 to the minus 2 to 10 to the 2 seconds. That's where we produce the electrons, and they recombine with the protons. So this is the nucleosynthesis. This is the Big Bang nucleosynthesis. It's a BBN. That's where the elements are formed. And I didn't show you exactly how to calculate it because it's just technical, but you can calculate exactly the abundances from exactly these considerations. At around 1 keV, that is around 10 to the 5 seconds. No, far from it. 10 to the 5 seconds, that's where photons fall out of thermal equilibrium. So this is the CMB photons. Reach a steady state. There are no more photons created or destroyed. CMB photons reach steady state. At around 10 to the 12 seconds, so this is the time of around 3 electron volts, that is the equilibration between matter and radiation. Okay, so this is around 10 to the 12 seconds. By the way, if you've seen their textbooks, like the first 3 minutes, you've seen that? That's exactly it. They're popular textbooks describing exactly. So if you've seen them, that is exactly what we talked about. 10 to the 12 seconds, that is raw matter becomes greater than raw radiation, and the universe became matter dominated. And that around 10 to the, this is already 4,000 years, 40,000 years, roughly, from the Big Bang. Yes. 12 to the 12 seconds. And then at 10 to the 13 seconds, right? This is where this is 0.1 electron volt.
Newtonian physics start to work.
What?
Newtonian physics start to work around that time.
We don't deal with Newtonian physics in this course, right? Then this is the CMB. This is the CMB. That's where we see. This is around 380,000 years from the Big Bang. That's where the CMB decouples from the rest of the universe. That's the equilibrium that we have.
When we think about
Now, then there came the Dark Ages. So this is redshift. This is redshift of 1180. This is redshift of around 3,600. Everything else is. And then the first galaxies occur at redshift of redshift of about 20. First galaxy.
How many seconds?
Calculate. We know how to calculate.
We don't know.
You know how to calculate. What is the age of the universe today?
13.8
13.7 billion years. Okay. Can I take a few more minutes of your time? Okay. So we're pretty much done with that. CMB. So I actually showed you that, right? We're seeing these fluctuations. I don't really have time to go over that briefly because we're already running. This is what we're seeing, these fluctuations. These are every point here is a black body radiation. The difference in colors, actually I have the figure, I think, yes. Each color represents a slightly different temperature. Delta T over T is 10 to the minus 5-ish. What do we do with that? When we see that?
Four patterns.
What?
Check this back.
Right.
What do you mean by the elliptic shape?
No, no. The elliptic shape is the galactic plane, right? The galaxy is here. This is the galaxy, right? This is when you look up in the sky, and that's what you're seeing. The galaxy, this is a galactic plane, so the galaxy is in the equator here. It's like a map of the Earth, just of the sky. Right? This is a satellite just looks around, sees, measures the temperature.
Wider.
Just the presentation. Okay. Now what do we do when you see something like that? You did see YLMs, spherical harmonics?
Yes.
Yes. We do take that and write it in terms of spherical harmonics. So we do write delta T over T sum, or LNM, ALM, YLM of theta and phi. And then we can plot the coefficient. CLM is, or CL, sorry, is ALM squared. This is something which you can do. In fact, it's slightly different for various technical reasons. What do we see when we do that?
K after the K.
What?
Probably not the K. And
You see something that looks.
The CL is not CLM because it's averaging over
It's
all
everywhere,
lines.
yes. We see something that looks like that. That's a multiple moment L, and there is an angular size. Now the first angular size, actually you know what it corresponds to. That's the angular diameter of the scenery. We talked about that last week. Right? But we do see plenty of other things. So this is called the Saffis-Wolf effect. This is called silk damping. Forget about that. What we see are these different peaks, which are very, very much pronounced. And what we have is the location of these peaks as a function of the L's and the height, the relative height of these peaks. Now I told you, what is the relative size says? We said that we had these oscillations, right? And there is a freeze out when the photons decouple. Right? So this freeze out, when there was a peak, we'll just be freezing on that. So the location of the peak tells us about the size of the universe essentially when there was this decoupling between the photons and the particles. What about the heights of this? It goes back to your point. Right? If you have if you have more matter, right, to have a stronger attraction. Right? So you have this would correspond to how much matter there is there. So if you have a more dense matter, it will get higher. Right? So the height of these peaks will tell us what is the energy density in the matter versus radiation inside. So we can scale that. That goes back again to what we have here. If there were other particles, we would see that imprinted on these fluctuations or these correlations between the fluctuations of the cosmic microwave background. That's another sort of independent proof of the standard model.
And do we get that there is more particles for that?
No.
No.
Well, what's the x-axis there? It's just the
X-axis is the multiple moment. It's the L.
L.
So it's a multiple moment.
And it's just an integer?
Yes, it's an integer.
So So why there are still people that think there is gravitons and
No.
all of those stuff?
Because there are error bars. You could put some particles which will be, in terms of energy density, they could be quite small. They can still fit into them. But you can put quite strong constraints on what the energy density could be. Right?
Mm-hmm.
That's why we got this cold lambda CDM. So lambda CDM is lambda cold dark matter. That's exactly what it comes from. Again, we don't really have time to discuss that. That's in a. I'm not sure if you're supposed to see that in a course of advanced astrophysics, or that's an extra course in astronomy. It's called extragalactic astronomy, and how we measure that and how that is correlated with the structure that we're seeing in galaxies in the universe. But that's a different story. Anyway, guys, we already took it's the last lecture. We've already took too much of your time, and hopefully it was enjoyable. Exam, as far as I know, is 4th of August. I will not be present here in Israel at that time. I'm traveling. So Akshay is supposed to come and answer questions if there will be any. I have not written yet the exam, so I've got no idea what questions are going to be. Feel free to speak about things that I don't know. Format will be the same format as in previous years, namely 4 questions, which will cover hopefully all the material or the subjects that we discussed during the semester. You can exclude the subject that we talked about today. We haven't had time to do it, I think, enough. Except from that. What?
How much time is
like all other years, I will put last year's exam with my suggested solution to the exam on the course's webpage. What?
3 hours?
I don't know if it was 2.5 or 3. I think 2.5 should be enough for it. Basically half an hour for questions plus extra half an hour. Questions are of the same type that you found in your homework. Normally I try to do with several sections. And it's not, I don't believe in, finding the physics, eureka during the exam. During the exam, you're supposed to show that you understood the physics that we talked during the semester, that you know how to use it. There is not, you don't have to memorize very long, lengthy derivations. Basic equations, such as geodesic equations, yes, you do need to know that. If you insist, you need to know that. If you don't insist, you definitely need to understand, to apply. But I'm not going to ask you to memorize this. What?
If during the test we find that you need some kind of parameters,
normally, all the questions, homework and test, I solve before I give it. Oh. So I know what is needed.
But maybe you have a different way of solving it using equations that you don't
do whatever you want, right? I know that they are solvable. I know that all the questions in the exam are solvable within a reasonable amount of time and without the need for a very complicated and sophisticated thing. And if there is something which I think is more than trivial or more than basic, maybe trivial is the right word here, is more than basic, then I provide it as part of the question. So you don't need to, you should have enough hints in the question. So if there is something which you get stuck and think you need some really formula that's not there, then likely you're doing something wrong. Likely you just need to go back and see where you got it from. Most of the parts of each question, you don't need more than 2-3 lines to solve. You just need to know what to do. Right? There is nothing really fancy there. You can solve it. The questions will be formulated in English because not all the students here are speaking. I can read Hebrew, and if you solve in Hebrew, I will check. I'm not. The deal is that Akshay is grading your homework. I am grading the exams. So they will come to my office, and I will virtually my office. I will not even be here present, and I will grade them. So yes, you can write in Hebrew if you feel more comfortable. But as you see, English is not the issue in this course. this is not there. Okay, do you have any further questions about the exam or anything else? I am here. I happen to be traveling on the 4th of August, so I'm here until then. I cannot guarantee that I will be in office every day or every hour that you look for me, and as usual, it's always a very, very bad idea to wait these questions to the last minute. So if you have questions, do not wait to the last minute. Come now or send me an email now, because if you come on Friday, when the exam is on Sunday, I may not be able to answer it, even if I really want to. So don't wait until the last minute. Besides, as usual, I don't know, is there anything else that you need to know? If not, then thank you very much, and I hope you enjoyed, and I wish you all success in the exam, and generally in the coming examination period. And, good luck.
Thank you very much. לסכם על הפרשים של הרצאה כללית. הפרשים האחרון של מה? לראות. כן. לא, מה זה?
זה מה שנראה, זה DL, זה CL כפול L, זה L.
עושים לכמה קבועים.
כפול איזשהו קבוע, כן. לא היה לי זמן לעבוד על זה.
אבל כאילו, בהקשר בפרשים שראינו שאתה
לא, יש לך
כל הקטנים.
זה רגע שבו זה...
לא, זה